Hi class, welcome back to another Math 105 video. In this video we're going to be talking about section 3.3, subtraction concepts, algorithms, and estimation. And so in our last video we were talking about addition, right? And we were talking about models from the really basic set model, which didn't get introduced so basically, but in terms of thinking about two groups that we put together, and then the amount in that final group is the result, the sum, and that's our meaning of addition. And then we went through a lot of other kind of models and representations. We looked at the number line model. We looked at some algorithms, including the standard algorithm, some place value addition algorithms, and even looking at base 10 blocks and how we would add numbers using our units, our longs, and our flats. And so we're going to roughly follow that same sequence here when we talk about subtraction. And so our models. Just like last time, roughly in order of sophistication, we have our takeaway set model, where we have one group and we take some amount away and we see what's left. And then our number line model, where we have a number where we're starting, and now instead of moving towards the right and adding, we'll move to the left towards 0 and take away some of that length. The concrete model is still going to look at our units, our rods, and our longs, and using our base 10 blocks. Trades first, where we do all of our possible regrouping at the beginning, and then a couple more missing add-end, counting up, equal additions, and then the standard algorithm. And so just like last time, I'll go through each of these in turn. So a takeaway model views subtraction as some set of objects being taken away from an original set. And so here we have a picture with 8 blocks, and we say, well, we're going to take away 3 of them. And so we had 8 to begin with, 3 get taken away, and we're left with 5. Right? And this is kind of the intuitive or approach that when you probably think about subtraction in your head, this is what you're thinking about, take away. But this is also the most concrete in terms of I have 8 blocks and I take 3 away, how many are left, right? This is the hands-on, really practical approach that we can use when we talk with children and the meaning of subtraction. The number line model, right, so like I said, addition is going towards the right. We add on more length, and so subtraction we're now going to think about as moving to the left. And so if we have 5 minus 3, we think of going to the right 5, and then to the left 3, and let me get a pen out. So we go to the right 5, and then we go left 3, and where we end up is 2. And so 5 minus 3 is 2, because when we move to the right 5 and then left 3, we get to 2. And it's really important that we remember this left and right orientation, because once we get to working with negative numbers in a couple weeks, or rather a few videos from now, what we're going to be looking at is this notion of left and right. And then take the opposite notion of a negative number is going to really hinge on this idea of left. And so just to foreshadow what's coming. Now, the concrete model uses base 10 blocks and even exchanging to carry out the subtraction problem. So suppose here we have 243 minus 61. Well, the first thing we can do is we know we can get rid of this 1 unit, and then I have to take away 6 tens. Well, I have 1, 2, 3, 4 that I can take away, and I still need 2 more. And so what we do is we replace this flat with 10 longs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I still had to take away how many more? 2 more. And so that means I'm left with 1 flat and 8 longs and 2 units. So my difference should be 182. And so this slide here, I talk about I can take that 1 and the 4 out, but then I have to replace one of those flats with 10 more of these units. not units, longs. So my flat becomes 10 longs, and I can cancel 2 more of them, and then we see that we're left with 182. And so these side-by-side breakdowns are just in case you're viewing the slides afterwards so that it still makes sense. Right, and so we can see how, at least from the set model to the concrete model, that's a really natural bridge, right? Because we're working with individual objects, but then once we get to place value and we can use place value understanding, using our base 10 blocks really enables us to interact with subtraction in a really concrete way. Now, trades first is going to be similar to our standard algorithm, except all of our regrouping will happen before we do any subtraction. And so, in this example, we have what? It's 122 minus 37, and I will go ahead and write this out. 122 minus 37. 122 minus 37. And so we can look at our hundreds, our tens, and our ones. We start with 100, 2 tens, and 2 ones. When I know at the end I need to be able to subtract 37 of them. Well, I don't have enough ones, so we'll regroup this to 110, and then this becomes 12 ones. And then if we can't take a 3 away from that 1, so this 100, we have to rebundle over, and we get 11. And so we have 12, and I'm going to rewrite these in a different color. Here we have 12 minus 7, and here we have 11 minus 3. And now both of those subtractions can happen. 12 minus 7 is 5, 11 minus 3 is 8, and so that means the difference between 122 and 37 is 85, right? We can check that by saying, well, 85 plus 7 is 92, plus 30 is in fact 122. And so that's what's happening here in this table, but they rebundled that 100 first into 12 tens, and then that 12 tens into 11 tens and 10 ones, and they rework it that way. And we get the final answer of 85. And so if you want to be able to read this table a little bit easier, this is where the subtraction line goes, right? So we have 122 minus 37 equals 85. And so you can see how we can kind of do these rebundlings at the beginning, but when we talk about the standard algorithm, we do it later on. We do it in the moment when it needs to happen. And suppose we have a student that's struggling to see that, or even for all students, I would highly recommend seeing this version first, where we now have, and so see that this model rebundles in the way that I had, right, where I rebundled 110, we rebundled 110 over, and then we rebundled the flat over. And so you can see two different ways of doing this. And that's often the case. Regardless of the method you're using, rarely is there a single way that you have to do the subtraction, right? Usually when we do a model, there are still choices. A particular algorithm still has choices that individual students are going to make differently. But this one here matches the way that I had done it, where I first rebundled one long, and then I rebundled the flat, and then we subtract, but we still get 85, right? And so that's the beauty of having children work together when they're doing mathematics, is because suppose I sit down and I rebundle it this way with my base 10 blocks, but then my neighbor, she rebundles it in the way that it was on the previous slide. We both get 85, right? We still get the same answer, but then we can sit and talk about, it's like, oh, well, why did you rebundle that way first? Or why does it matter which way we rebundle, right? Like, it really generates a lot of this productive discussion. And then the missing addend model uses the fact that addition and subtraction are inverse operations. And so what you can do is for any subtraction problem, you can convert that to an addition problem. And so, oh, and there's a little space that should be there, but the subtraction problem, 8 minus 3 equals blank, that red square, is equivalent to thinking, what number must be added to 3 to get 8? And so in this example, the missing addend is 5 because 3 plus blank, or 5, equals 8. And so we can convert, or I'll use this word, translate subtraction into addition. And I think naturally our instinct is, once we move to subtraction, we're like, no, we want children to be subtracting. We want you to be subtracting. Don't be going to going back to addition. But I really think it's important that by going back to addition, two things are happening. First, we're using strengths. So if we're already comfortable with addition, why not use that? Why not leverage that strength? But second, it actually is showing a really good insight into the child's understanding of the relationship between subtraction, and addition, right? They're two very intimately and closely related ideas, and I think we would be doing a disservice if we treated them as completely separable. And then a third bonus one is, there are still times where subtraction is easier to do the missing addend. Like if I had 307 minus 298, I would just look at, well, 298 plus what gives me 307? Well, 2 and 7 is 9, so the difference is 9. I'm not going to subtract. I'm not going to be doing any rebundling. I'm going to find the missing addend. And so this is what it would look like in both that set model, where we have 3 plus something gives us 8 in total, or we have 3 over, and we know where 8 is. And so in the number line model, what we're looking at is, let me not use blue. What we're looking at is this distance. This is our unknown, right? And notice that helps us see that the distance between 3 and 8 is 5. Distance between 8 and 3. And so while we have these kind of algorithms or models, in many ways we're going back to our really foundational models of set and number line, or base 10 blocks. So you could do a missing addend with base 10 blocks. You could do it with our set model and our number line. So counting up is in some ways connected to the missing addend, in that we're still doing the translation back to addition. So we're still translating. To addition. But we're going to count up from our subtrahend and or up from our subtrahend to our minuend, or give me a sec, I have to think. So we count up from our subtrahend to our minuend. So if we have, this is just an aside, 7 minus 3, this is our minuend, and this 3 is our subtrahend. Just know that those have words. I would say they're not super common. My face is in the way. We don't use them a ton, but it is important to know that they have names. The minuend is the larger number from which we're subtracting, and the subtrahend is the thing that's actually being subtracted. And so in counting up, we count up from the subtrahend to the minuend. So suppose we have 1,217 minus 427. And so how this would look in terms of counting up, well, we'd have 427, and I'd be like, well, I know that that's 73 more, gets me to 500, and then I can go up 500 more to 1,000, I can go up 200 more to 1,200, and then 17 more to 1,217, which means that these pieces that I added on, 500 plus 200 plus 73 plus 17, so that's 700, 73 plus 7 is 80, 90, 790 is our difference here. So you might have been able to see, oh, well, for 500, I could just add 700 to get to 1,200, Or you might have a student that goes 427 plus 3 is 430, plus 20 is 450, plus 50 is 500, right? So there's lots of choice here. Because what constitutes a nice number is going to be different for everybody. But that's the nature of the counting up model. And so here they do 50 minus 11. And this is actually really commonly done when you're getting change, right? If you're using cash, because anyone ever uses cash. But if you're using cash, you pay 11. The cashier says it's $11, and you have a 50. She's going to go 12, 13, 14, 15, 20, 30, 50, right? She's going to count up as she gives you the money, or he or whoever they are, right? The cashier is going to be counting up. Now, equal additions is going to leverage the fact that subtraction is the distance between two numbers on the number line. And as long as we shift both the subtrahend and the minuend in the same direction by the same amount, our difference won't change. So for example, suppose we have 255 minus 163. Well, we could add 7 to both of those. So on a number line, what that looks like, so here we have 253, or 255 rather, and then we go left, 163. It's like, well, where do we end up? Well, what we can do is we can shift that whole picture to the right. So now we have 262, left 170. But in both cases, this distance between the endpoints is preserved because both arrows got shifted in the same direction. So both arrows shift right 7, and then they shift it to the right again by 30, and so now we're at 292, 200. And so what's interesting to see there then is it true that the distance between 292 and 200 is the same as 170 minus 262? Is that the same as 255 minus 163? So maybe take a second and type that in your calculator and make sure that those all do in fact equal 92. And I hope what you did find is that 262 minus 170 is 92, and 255 minus 163 is 92, right? And so since we're always shifting by the same amount, that distance between the endpoints, which is the result of our subtraction, is the same. And so as long as you're adding the same to both, or you could subtract the same from both, your difference won't change. But notice how we get to this final version where we're working to getting the hundreds place the same in both. And the nice thing about that is now all of our subtraction is only happening within a single place value, because 92 minus 0 is 92. And so we just have 200s take away 200s. So if you remember in our addition video, we had our join result unknown, join change unknown, and join start unknown, right? Because we had a join or addition problem, and we switched between which of the three things we knew, right? So we had our result, our change, and our start. And so we took turns in each of those, one of those missing. And so really we're going to have the same three structures for subtraction, except now we're going to have our something, something, and something. So instead of a join, we talk about separating. So Connie has 53 marbles and she gives 35 to Juan. How many marbles does she have now? So we have a separate and the result is unknown, right? And so use any number of strategies. This is just a way to classify subtraction problems. So we had 3 classifications for subtraction, or for addition. Let's see how many we have for subtraction. The separate change unknown is where, again, we know our initial amount, and we have our result is known, but we don't know our change, right? The amount that it's changing by. So Connie has 53 marbles. She gave some to Juan, and now she has 18 left. So you can imagine she just reaches into a bag and hands them to Juan, and it turns out he has some number now, and that's what we don't know. Separate start unknown. And so I would say roughly in order of increasing sophistication, Connie had some marbles and she gives 35 to Juan. Now she has 18. How many marbles did she have to start with? And so this really could have 2 approaches. One would be guess and check. But separate start unknown really depends on this relationship between addition and subtraction. Because the way to solve this is going to be 18 plus 35. Right? Because we knew how many she had left and how many she gave away, and so how many in total. So in some ways, this is a join result unknown, which when we talked about addition was kind of the least complicated. It's just the fact that we have to be able to translate from subtraction to addition to see this that really gives us some of the difficulty. Right, because even separate result unknown, we don't have to be able to go to addition. Separate change unknown, just like we talked about counting up, you could count down. 53, give away 3, and I'm going to model this. And so, just like there was counting up, you could talk about counting down. 53, you subtract 3 to get 50. You subtract 20, or actually 30, to get down to 20, and you subtract 2 to get 18. And since we ended up where we started with, we actually have minus 25. Nope, 35. And I often use this kind of writing, where I just write them in sequence, but you could also say, well, I'm at 53, and I have some number down to 18, and what's happening is I jump minus 3 to 50, minus 30 to 20, minus 2 to 18, and then here we have 3, eraser, 3, negative 3, negative 30, minus 2, it's 35, right? And so that's another way we could show this subtraction. But ultimately, it's no different than counting up. So let me pick a different color. Orange. Counting up. Start at 18, you can go up 2 to 20, up 30 to 50, and up 3 to 53. So we have 2 plus 30 plus 3 is 35, right? And so there's at least 3 different ways we could do this separate change unknown. Separate start unknown, you could convert to addition. That's not the only way you could do it. Particularly think about a number line. I have 18, and I know I went left 35, and I don't know where I am. And so figuring out through counting up 18, count up 35, but once we're counting up, right, we're really doing a join. So that's how we can classify the 3 subtraction types. So there are 3 addition types, 3 subtraction types, and then we're going to talk about these CGI types when we get to multiplication and division, and there will be more than 3 in those, because it turns out that the last 2 operations tend to be a little bit more complex. So basic subtraction facts. So this is our subtraction table, so just like we had our addition table. And let me go ahead and move my picture. We're going to come over here. Going on a trip. And so just like we had our zeros facts for addition, we have zeros for subtraction. That's all of our minus 0. So when you subtract 0, it doesn't change. Counting back facts, that's where it's relatively straightforward and easy for a kid in their mind to keep track of counting back 3, counting back 2, and counting back 1. And so that's minus 3, minus 2, minus 1. The take all facts are all of these on the diagonal. When you take a number away from itself, you have none left. So this is like your 4 minus 4 or your 17 minus 17. When you take them all, you're left with none. Your neighbor facts, so this is where they're close to your take all facts, and so those two operate off of each other. And it's not like you would be like, kids, let's use our neighbor facts, or, well, actually you might. I take that back, right? And so this is particularly a way for kids to organize their subtraction and start to find patterns in the subtraction process, because we don't want them to think of this as 20 plus 19 plus 18 plus 17 all the way down to 1. So we actually know the formula for the sum of the first n numbers is 20 times 21 divided by 2. And so what's that? Let's do that real quick. 20 times 21 divided by 2 is 210. We don't want them to be thinking of this as, oh my goodness, I have 210 facts to memorize just to get subtraction up to 20, and then as soon as we go to 30, we're going to have even more, right? We don't want it to be that sort of, all of these are these disjoint facts, but we have a set sort of processes that we can use to get to all of these facts. So our neighbor's facts are the ones that are close to the take all, right? So if you have 17 minus 17, that's none, but if you have 18 minus 17, well, that's almost all of them. You have 1 left over. Or 19 minus 17, you have 2 left over, and so on, right? So you could think of it either as going across, or perhaps thinking of it this way. 13 minus 13 is 0, 13 minus 12 then is 1, and 13 minus 11 is 2, right? And so going up in the table. But again, these different directions, these different choices are going to make different sense to different students, and we give them those options. Our takeaway tens facts, that's where we really leverage place value. And so place value is really what's at play here. 19 minus 10, you're left with 9. 14 minus 10, you're left with 4, and so on. Your back to tens facts is this diagonal here. 19 minus 9, get you back to 10. 16 minus 6, get you back to 10. And so it's the subtraction that gets you back to 10. Right, and so it tends to be that our tens facts tend to be helpful because we can use those to get us to 10 is a nice number to work with, right? And so we tend to use that as a benchmark number. And then we have our take half facts. So 8 minus 4 is 4, 10 minus 5 is 5, 14 minus 7 is 7. And kids know that because we had our doubles facts in addition. 4 and 4 is 8, 7 and 7 is 14, 9 and 9 is 18. And so we know that we can just do half of that back to get where we want. And then our up to tens facts are just these ones where if we're taking, say, 11 minus 4, you need 7. And so it's 11 minus 4, 7, you go up 3 to 10, and 1 more is 11. And so thinking about up to 10. And so then once we break it down, we really have, 8 strategies, and then only a handful left over that aren't colored at all. And so that takes 210 things and reduces it to 40, maybe. Not too bad. Okay. So a formal discussion of subtraction. And now remember, when we had our formal discussion of addition, we were talking about sets and properties like associativity, commutativity, and things like that. And so first we'll define subtraction. So for any whole numbers a and b, such that a is greater than or equal to b, so a minus b is the unique whole number c, such that b plus c equals a. You're like, well, that's lovely. What does that mean? So I need two numbers, one bigger than the other. So a is our minuend, b is our subtrahend, and we have, say, 7 minus 4 equals something. And so this definition of subtraction says, well, a minus b is that unique whole number c such that 4 plus c is equal to 7. And so the very definition of subtraction relies on addition. Oh, my face is in the way. I'm going to go back over to this side now. So here, our very definition relies on addition. But it's also important that because we're working with whole numbers, and remember those are the numbers 0, 1, 2, and so on, subtraction is only defined when a is bigger than or equal to b. So the smallest difference we can get when working with whole numbers is 0. We can't do 4 minus 7 yet because we don't have a notion of -3. And so -3 will come once we get to the integers and once we talk about adding and subtracting with negatives, which is going to come in about a chapter. And so it says it can be shown that if a is less than b, so that is if we have, if a is 3 and b is 7, 3 minus 7 is not defined on the whole numbers. And whenever you apply an operation and you don't get the whole number back, we have this notion of closure. So subtraction is not closed on the set of whole numbers. And so closure says anytime you take two numbers from a set and subtract them, you'll get something back. And that doesn't work here because we have to take a smaller number from a larger number. Now that's in contrast to once we get to negative numbers, we will have closure because no matter what number it is, you can subtract another one from it. You might get a negative number, but you're going to get a number that's defined. And so this is the idea of closure, is if you subtract any possible number from that set, from any other possible number, whether or not they're bigger or smaller, do you get a number that's in that set? And so this addition is closed. It doesn't matter what you add together, you're going to get another bigger positive number. So addition is closed, but subtraction is not. And then we're going to continue this when we get to multiplication and division and talking about these things. So here's an example, 3 and 5, 5 minus 3 equals, I have a typo there, that's good. 3 minus 5 so A is 3 and B is 5. And so C is 5 minus 3, which is -2, which is not a whole number, so it's not closed. And then just like in the last one where we concluded with some mental math and estimation, I just want to give you a couple of these mental math strategies. Breaking up and bridging, and suppose we have 74 minus 26. Well, we can go ahead and shift. So what we do is we ignore the word shift, that's not the word I meant. What we're going to do first is what we're going to say, well, 26 is 20 plus 6. And so I'm going to do 74 minus 20, which is 54. And then I'm going to subtract the 6, which is 48. And because those two numbers came from here, we know that our result, 48, is what we wanted to see. So this is this notion of breaking up, because we separate by place value. So we had 10s and our 1s, and we got to our solution. Trading off. So suppose you have 74 minus 26. Well, what we can do, just like, remember when we talked about our number line, as long as we shifted those numbers, 26, 74, as long as we move those two endpoints at the same distance, we're not going to change. And so this, how you can read this, 74 minus 26 is the same as, add 4 to both of those, we get 78 minus 30. And now we can do 70 minus 30, which is 40. 8 minus 0, 48. So we essentially just shift those numbers up so that we have pretty ones and ones that we can just do a subtraction by place value. And then the last one, dropping zeros. And so this really, I don't love the name because you don't drop them, they don't go anywhere. But we're using place value. So we have hundreds, and then we have tens and ones, but because they both have no tens and no ones, we can just look at 74 minus 6, which is 68 hundreds, which looks like that. So not as many mental math and estimation strategies, and I'm actually going to not talk as much about estimation once we get to multiplication and division, because I really want us to focus on the models, our different strategies for subtracting, and really starting to think critically about why they work. So what's going on behind the scenes that makes them work? But that is the end of subtraction. I'll see you in the next video, everyone.